Hello and welcome to Water Quality. In this video, I'm going to go over an example using information from some previous videos, and here we're going to look at what happens when ferric chloride is dissolved into water, and we'll solve for the pH. Okay, so here I have written out the reactions that we developed in the previous lecture. So first of all, the first reaction is the dissolution of ferric chloride into its ferric iron and chloride constituents. So that's our first one. And that's a one-way reaction. It's going to completely dissolve. The solubility limit for chloride is pretty high, so it's going to completely dissolve in this case when only 10 to the minus 4 moles per liter is being added. And the next two reactions are the ones that we looked at in the previous videos. So here, ferric iron ion is being treated as a diprotic acid, so we're ignoring the FeOH4 minus, and also in this problem, we're assuming that there is no ferric hydroxide solid forming. And then at the end we're gonna check that assumption. So okay, and then also no FeOH4 minus. Okay, so I've already written out the reaction. So the next step, I'm going to write the mass balance equation, which is the CTFE, where we kind of account for all of the iron species that are dissolved in the solution. So we have free ferric ion, and then we have the FeOH2 plus, and we're looking at the concentration of that, and then the FeOH2 plus. And this is all going to add up to 10 to the minus 4 moles per liter, which is equivalent to how much ferric I added initially. Okay, so the next step is to write out the charge balance. And on the positive side, I have hydrogen ion. I have, let's see, I'm going to write out this one next, FeOH2 positive, and that's a positive 1 charge, so we don't need to put a constant in front of that species. And then I have the next complex, which is FeOH2 plus, and then next I have the free ferric ion, which is Fe3 plus. And then on the other side of the equation, I have hydroxide, chloride, and as I said before, I'm going to ignore the FeOH4 plus. I can write it in still, FeOH4 minus, and then just cancel it out. And that's a pretty good assumption to make because I'm adding ferric to water and I know it's going to react with hydroxide. So I know that the pH of this solution, the resulting solution, is going to be pretty low, and the FeOH4 minus is only important at very high pHs. Okay, so we're treating this as a diprotic acid. So in the next step, I'm going to replace some of the species with alpha values or alpha expressions, and I'm solving for pH. So this is my variable, hydrogen ion. And now I'm going to substitute this for an alpha times CT expression. And let's see. Okay, so we need to identify which alphas go with which species. And so I start with the most acidic, and that is going to be my alpha naught. So that is our 3 alpha naught times CTFE. Okay, and then the next least acidic, and that's here. So I have 2 alpha 1 times CTFE. And then finally, this one is going to be alpha 2 times CTFE. Over here, I'll make a substitution KW over H plus. The chloride actually is going to be equal to 3 times the CT value because for every ferric that's released, the original compound will release 3 chlorides. And that's it. Okay, so I could start making substitutions for the alphas here. And so I'm going to have, let's see, Ka1, Ka2. And I'm going to put all of these iron species together. And so let's see, this will be 2 times Ka1 times hydrogen ion, and then plus 3 times H plus squared, and then I'm going to factor out the CT value. So this is what I'm doing here is I'm putting all 3 of these together because the denominator is the same in all cases, so it just reduces the amount of variables in the equation, something we can all appreciate. Okay, so that's that. So that's my 3 iron species all put together, making substitutions for the alphas. And here the Kw is 10 to the minus 14. I did not forget the hydrogen ion. It's coming, it's coming, it's right over here. And then 3 times my CT. Okay, so I want to make all the numeric substitutions at the same time. I guess I jumped the gun on the Kw, but that's okay. So here we have 10 to the minus 14 over H plus, plus 3 times 10 to the minus 4. And over here, H plus squared. I'll go ahead and put my H plus right here. And then plus 10 to the minus 2.16 times H plus 10 to the minus 2.16 times 10 to the minus 4.58. Okay, let's go ahead and start putting these in. 10 to the minus 2.16, 10 to the minus 4.58, plus 2 times 10 to the minus 2.16 times hydrogen ion plus 3 times hydrogen ion squared. And then this is 10 to the minus 4. So I put this into a solver. I think I actually may have used my Excel spreadsheet. If you're going to be solving a lot of these, you want to come up with some really good solving methods. Solver on the calculator works great. You can also write a MATLAB code or an R code, or you can use a spreadsheet. So I got 10 to the minus 3.98, or a pH of 3.98. But this is assuming that we don't have any ferric hydroxide solid. And so that is something that we need to check out. So let's go ahead and do that. And I think I'm just going to carve out some space over here so I can show what that looks like.